Okay, let's continue on with our investigation of limits and look at a little bit more complicated equation, but it's no problem for us. We're going to be able to do this limit and then look at the table. So we have the function f of x equals 13.2 times e to the power 2.56x all over the quantity 1 plus 1.2 e to the 2.56x. And we're asked to complete the following table using Mathematica, Wolfram Alpha, Desmos, or our graphing calculator to help us do the calculations. Of course, we won't do this in our head. We're going to plug in x equals 0, 1, 2, 20, 200, and 2,000. And based on what we see in the table, we're going to answer what we think happens to f of x as x gets larger and larger. So what this question will essentially be asking us is to numerically determine the limit as x approaches infinity of f of x, because we're told x gets larger and larger. It's not approaching a specific number, it's just getting bigger and bigger and bigger. So we start with like a pretty small number like 0, 1, and 2. It's almost like not that relevant, but we're just looking for a pattern. We'll look at 20, 200, and 2,000 to see like if we can figure anything out. So again, I'm going to be taking x equals 0 and plug it in everywhere. So I'll just like make sure you understand. So this is 13.2 e to the power 2.56 times 0. I put 0 in for x all over 1 plus 1.2 times e to the 2.56 times 0. Okay, so when I put this all in, and e to the 0 power is 1, so this is actually not like very complicated to plug in, we're going to get 6. Okay, when I take it in the calculator, I get 6. Okay, because that's 13.2 over 2.2. All right, then I plug in for 1, and I get 10.3. I plug x equals 2, and I get 10.9. I plug x equals 20, I get 11. I plug x equals 200, I get 11. And then I plug x equals 2,000, I get 11. You know, so just based on what we see in this table, what do we seem to think is happening as x gets larger and larger? Well, it starts at 6, that's pretty far away. Then it quickly jumps to 10.9, and then even when x is 2,000, we're already like 11, 11, 11. So based on the table, I would guess that as x gets larger, y goes to 11. That sort of seems to be what's happening, right? And we should double check and make sure, using another method, that this is in fact what's happening. So let's look and plot and see in Desmos if that's the same thing. So what I'm going to do is I'm going to take the equation here, plot it in Desmos, and like I told you in the previous video, it's very important to always pay attention to the scale on the axis. And then because what we're interested in this example is what happens as x gets larger and larger, I'm going to make sure that I zoom out relatively far and that the values on the x-axis are able to get larger and larger, and that values on the y-axis are visible. So on your graphing calculator, you're going to have to play around with the window a little bit. Okay, so we get rid of this, and then we're going to put in the one that we're looking at now. So let me type it. Did it wrong. Parentheses, as I told you guys, parentheses is everything. Okay, so here's our graph, and you're like, oh, I can't see it. Something's wrong. It's just this little subscript I guess it didn't like. Okay, here we go. Right, so then now I'm going to change the settings because I want to see the values on the x-axis up to, say, at least 2,000. Okay, so there we go. There we go. That looks a little bit better. So we kind of zoom correctly, and it looks a little weird, right? Like I told you, sometimes the calculators can't handle, like, I bet if you took your calculator and you tried to plug in x equals like 1,000 or 2,000, it might fail. This software is just not powerful enough. But it lets us have the idea for what's happening in the sketch. So that's why we can compute things three different ways, like numerically, graphically, and algebraically. We triangulate our answer to make sure that we're correct. All right, so based on this graph and using an appropriate scale, I would probably make a sketch that looks something like this. Right, so this, on the y-axis, it's only going to go up to 11, but on the x-axis, we could at least go out to, like, say, 200, and then after that, it just kind of like fell off, so we're not going to go out too far. But it seemed like it was looking basically like this, didn't it? Let's just double check. And then on the other side, well, not clear exactly what's happening. It kind of just seems like it's going like that or something, right? But the part that we care about is really this part, because what we want to know is what happens to y. Oh, sorry, I forgot. What we care about is the part that's circled there, because what we care about is what happens to y as x gets bigger and bigger. Okay, so in other words, I want to know, like, what happens, this is x, as x goes to infinity and gets bigger and bigger, what happens to y? It seems like y approaches 11, okay? So, yes, this does support our conclusions because we're seeing the same thing, okay? So, for large x, the y is around 11. Okay, so make sure you use the proper scale. We're looking for what happens as x gets large. And we can say now that the limit as x approaches infinity, so this means as x gets big, then y gets close to 11. Okay, so we say that the limit is 11. And we should check this one more way, which is algebraically, to make sure that we're correct. So I know, like, not everybody is super strong in algebra, but if you are, you can do it like this too. So let's just check one more way. Okay, so we want to know the limit as x approaches infinity of our function. Let me write down the equation. Okay. 13.2 e to the 2.56x over 1 plus 1.2 e to the 2.56x. So when you're computing it algebraically, you can, like, try to plug in the value, but if I plug in, like, a huge number on top, I would have a huge number on top, huge number on bottom, I'd have a huge number on bottom. So this would be approaching infinity over infinity, which, just like 0 over 0, is undefined. So I can't, like, make a conclusion based on that. So what I'll do is, similar to what I did before, I'm going to rewrite this in a way and hope that then I get a value out that's defined so that I can plug x in. So the thing that's causing me the problem is the e to the 2.56x. So then I have the idea, okay, I'm going to divide top and bottom by e to the 2.56x. So totally I'm just multiplying by 1. I'm not changing anything. But if I do this, I can rewrite the limit. So on top, I'm just going to have 13.2 because the e to the 2.56x will cancel. And then on the bottom, make sure that you distribute this properly so that I would have 1 over e to the 2.56x plus 1.2, because on the 1.2, the e to the 2.56x cancels. So if you want, you can try to take the limit again. And the only place where we have the x in the equation is here. So now x is going towards infinity, so I have 1 over a big number. 1 over a big number is a small number, so this little bit will go to 0 as x approaches infinity. So I can say that this is equal to 13.2 divided by 0 plus 1.2. You'll notice I didn't write limit as x goes to infinity now because I took the limit. So as x approaches infinity, this quantity approaches 13.2 over 1.2, which, if you simplify, is equal to 11. Okay, so we see that 11 is the correct answer. And numerically, graphically, and algebraically, we find that the limit as x approaches infinity of f of x equals 11. So the methodology is the same, but when x approaches infinity, instead of plugging in values close to 4, you plug in or graph values that are quite large as possible, at least 100 or 1,000 or something like that.